numerical example. So the first here, the first example is find ft given that fs equal to s squared plus 12 over s times s plus 2 s plus 3. So this is the function in the frequency domain, which is the Laplace transform of the function ft. This is fs is the Laplace of ft, and we want to find ft again. That means we need to apply Laplace inverse for fs. So Laplace inverse for fs here, I need to apply Laplace inverse for this one, but it's not easy for me now with this form of the function to find it in the table. So if I go back into the table, and if I have s, even I have 1 over s here, you can see s plus 2, s plus 3, but you cannot go directly to convert. For example, the 1 over s, you said it is ut times exponent negative 2t times exponent negative 3t. It's not like that one. Even these variables are there. You can find similar variable in the, or similar form of the function in the table, but you cannot apply the inverse Laplace for some function which is multiplied. So you have s times s plus 2, s times times s plus 3, and you have also numerator here. So how we can find this inverse Laplace? We need to apply Laplace inverse, the partial fraction. So I want to check first how many poles do I have here. So we have 3 poles at s equal to 0, and at s equal to negative 2, and at s equal to negative 3. That means what are the values which make the denominator equal to 0? Either s equal to 0, or s equal to negative 2, or s equal to negative 3. So these are the poles of our function. They are 3 poles, real numbers and distinct. No similar poles, no imaginary number, no complex number. Okay, so in this case, it's easy. You just need to apply the formula here, which is you put a over the first root plus b over the second root plus c over the third root. After you apply this, formula, you need to calculate or determine the value. What is the value of a? What is the value of b? What is the value of c? Okay, so how to find this one? As we did here before in this part. So if you want to find a, you need to multiply the denominator or the pole of a times the function, and you substitute for each s by 0, which is the value of the poles, or the value of the make s or the denominator is equal to 0. We can see here. So we have a over s plus b over s plus 2 plus c over s plus 3. You may ask, where is this part? This part will be considered when we do the calculation for the multiplication of fs times the value of the pole s, for example, or s plus 2 times fs. So in this case here, we are going to consider the value of this numerator. Okay, so how to find a here? The first one, a is equal to s fs. When s equal to 0, you will just multiply s times the function here. This is our function, which is if you multiply by s, then you substitute for each s by 0. That means when you multiply by s, this s will go with that s. Then this becomes 0. So this is 0. This becomes 0. This becomes 0. So you have 12 over 2 times 3, which is 6. So 12 over 6 is equal to 2. So this is the value of a. Then you move to the value of b. B also you need to substitute, to multiply the pole of b here, which is the pole of b is s plus 2 times fs. So that this function here, you are going to multiply by s plus 2. So s plus 2 here, this s plus 2 with that s plus 2. So the rest here, you have s squared 12 over s times s become s squared plus 3. So you have s squared plus 3, and you have here s squared plus 12. You substitute for s equal to 0. For s is equal to negative 2. So when you substitute for s equal to negative 2, you are going to find the b is equal to negative 8. Then you move to find for the third part here, which is s, 3 over s plus 3. You are going to multiply by times s plus 3. So this s plus 3 will go with that s plus 3. Then you substitute for each s by -3, which is the value that makes this denominator is equal to 0. Okay, so we have to substitute here -3, and -3 squared will give you 9. Then you have plus 12. Over here you have -3 plus 2, it gives you -1. Here you have -3. -3 times -1 is give you 4. Okay, I mean 3. So 9 over or 9 plus 12 over 3 will give you 7. After I find the values for a, b, c, that means I can find my new function. This is the original one. What I do here is just I convert it into a partial part. Okay, so it's become 2 over my which is the value of a here, equal to 2 over s minus 8 over s plus 2 plus 7 over s plus 3. So I have 3 parts here. If I add these 3 parts by finding some common denominator and then substitute, I will get the same answer. So this function is equal to this function, the same. Only this come as a part, like if you have 1 is equal to half plus half is equal to quarter plus 3/4. It's the same. So here we have the function consists from 3 parts. Now it's easy for me to find from the table what is the inverse for 2 over s. 2 over s, the inverse will be 2 ut, because ut is 1 over s and they have 2 here, so it's become 2 ut. Then what is the inverse for 8 over s plus 2? So it's become 8 exponent -2t. Then what is the inverse for 7 over s plus 3? So it will be 7 exponent -3t. Okay, so this is 7 exponent -3t. This is 8 exponent -2t. And here we have 2, all multiplied by ut because Laplace is greater than or equal to 0. Okay, so this will be the inverse Laplace transform for this Laplace transform. So this is the first case, and we said the first case you have multiple or different pools and with real value. The second case will be and this actually the same example, you can just go through. I mean, it's not okay. I will talk about this one because this just to show you how to use the property of derivative or derivative forms to solve this differential equation. Okay, and this is one of the main application for Laplace transform, which is how to use Laplace to solve differential equation. Okay, so in this instead of giving you like this function, you may see this I mean directly function and you ask to find the inverse Laplace. This like this one type of question, you are given this inverse, I mean Laplace transform, and you will be asked to find what is the inverse Laplace. So you are going to apply this partial fraction directly to solve from the table. Then the second method here, you will be given such differential equation. So this is differential equation, which is d squared y over dt squared plus 12 dy over dt plus 32y equal to 32 ut. And you will be asked to find or to solve this differential equation. Solve means, as I told you before, the solution for differential equation is not a variable. I mean, it's not a value. It's not like I said when I asked you, I gave you x squared plus 2 is equal to 0. Then I ask you solve this equation. You will say x squared equal to -2, then x equal to plus minus j set 2, for example. This is the solution, is give you a value of a variable. When I say x -3 equal to 0, that means x equal to 3. So this is the solution for the normal ordinary equations. But if you have differential equations, so the differential equations here, the solution for this differential equation is to find what is the y here. What is the function, the original? I have equation here consists from the second derivative, the first derivative, and the function here. But I don't know what is the value of y of t here. So the solution for this differential equation is to find what is yt. Then this will be your solution. What is xt? That will be your solution. It's not a values. Okay. So how to use the Laplace to solve this equation? That means the question is how to find yt for this function. If you given this function, d square y over dt square plus 12 dy over dt plus 32y equal to 32 ut, how to find the value of yt from this equation. What we need to do, we are going to apply the derivative forms for theorems from the table of Laplace. So you can see here in the Laplace table, we have three theorems which is related to, which are highlighted here with the red color, to use to convert for the derivative function into Laplace transform. So if you have d over dt, that means the first order derivative, so the answer will become sfs minus f of 0, which is the initial condition here. If you have the second derivative, I mean like d square over dt square, so this will give you s square fs minus the s times the initial condition of 0 and initial condition of 0. Then you have, if you have to the power of n, so this will give you Sn Fs minus. So these initial conditions actually either will be given to you or will be assumed as 0. If assumed as 0, so what you need to do only, you need to use this part, Sfs, S square Fs, S cubic Fs, S to the power of 5 Fs and so on. And this all initial condition will be ignored because they are equal to 0. And this is what we usually apply for when we talk about the transfer function of any circuit. So as you can see here, this is the function. It's easy. I can convert it from the, from the time domain to the frequency domain. This function now is in the time domain because you can see here d square y over dt square. We have time here. Or dy over t. This one y small, that means it is yt. Okay, you have here ut. So the first you need to do in order to solve this differential equation, the first step, as you can see here in this list, take the Laplace for both sides of the differential equation. This is the first step. You need to apply Laplace. Laplace for left side, Laplace for right side. Then after you apply Laplace here, you need to rearrange the resulting function to be as a function like ys here. I mean both ys in one side and both the rest in the other side. So ys is represent your response or your solution for differential equation will be yt. So first we need to find ys. Then you need to apply Laplace inverse for ys in order to find the value of yt. This is what we are going to do now. Okay, so how to write this equation again by using the Laplace? So you just replace each derivative by 1s. I mean, if you have the first derivative, so it's become s. If you have second, so it's become s squared. If you have third, it's become s cubed and so on. So you rewrite the equation here. It's become like this part. It is s squared. Then y of t here, actually we do not write it, but it's by default it is when you have small letter, that means it is y of t, because you drive it to t, so it is y of t. You drive it to t, so it's y of t. Okay, so yt here small will be converted into the Laplace by using Laplace into ys, capital letter with s operator. Okay, then the second here, as you can see here, the initial condition are all 0. See the initial condition of yt and dyt given by y0 equal to 0, y prime 0 equal to 0. So since the initial condition are 0 here, as mentioned in the question, are 0, only we need to consider the derivative value with the function. So we have s square ys, 12, this dy over dt give you s, ys, plus 32 yt, it gives you 32 ys. Then on the right side, we said apply Laplace for both sides. So we have 32 ut. So what is the Laplace for ut? It is 1 over s. So this is the new equation that we have in the frequency domain after we apply the Laplace for this function. Okay, then you need to use this function to rearrange this function. So we take ys on one side, and we put the rest on the right side. So ys here, from this one, for example, it is like ys, and you open this one. So we still have here s square plus 12s plus 32. So this on the left side equal to 32 over s on the right side. Now I want to find what is ys. Ys will equal to 32, which is the right side, divided by these variables or these operators. So I convert it to this side, and I still have s from the right side here. So this is the new ys function, or the resulting ys function that I have. I simplify this ys function. I solve these two roots, or I write the polynomial for these two rows. So s squares become s plus 4 times s plus 8. So this one s plus 4 times plus 8. If you open, it gives you s squared 12s 32, and I still have one s here. So now I have this function which is ys. Ys equal to 32 over s plus 4 times s plus 8. So now, can I find the Laplace inverse for this function in order to find the solution, which is yt, directly from the table? I cannot use it directly from the table. Why? Because I have times here. S times s plus 4 times s plus 8. It's not separate part. You cannot apply for a function which is consists of multiple roots multiplied by each other. Okay. What we need to do, we need to apply partial fraction method. So partial fraction, the one that we have here, all pools are different and are real numbers. The first pool is s equal to 0. The second pool is s equal to -4. The third pool is s equal to -8. So 0, -4, -8, all are different and all are real numbers. So just substitute for them in this function. I assume the numerator value, which is k1, k2, k3. You can say a, b, c. You can see x, y, z. Any number that you want. I mean any variable or any letter you can substitute here. A1, B1, A2, A3, B1, B2, B3, whatever. Then you need to calculate this magnitude or these gain values. How to calculate? Same like the previous example. We have k1 over s, k2 over s plus 4, k3 over s plus 8. You just find the value for k1 equal to 1, k2 equal to -2, k3 equal to 1. Then the function will become like 1 over s minus 2 over, because I have -2 here, so it's become like minus 2 over s plus 4. I have plus 1 here, so it's become 1 over s plus 8. So this is your transfer function in the partial fraction form. Now it is easy for me to use the table to find the inverse for each part. So what is the inverse for 1 over s? It is ut. What is the inverse for 2 over s plus 4? It is 2 exponential -4t. What is the inverse for 1 over s plus 8? It is exponential -8t, all multiplied by t. So this is ut here, represent the solution for your differential equation. Okay, where is the differential equation? This is the differential equation. So in the exam, if I give you such differential equation and I ask you to solve, that means I need you to find what is yt here. If I said d square g over dt square, that means I want you to find the value of gt. I say dh square or dh cubic over dt cubic, that means I need to find the value of dht. So the solution for any differential equation here represent what is the value of this function. Clear? Any question until here? Or I will ask. If no question, I will ask.
Sir,
Yes.
can I use normal partial fraction instead of this method?
Which method?
Because this method is using the what is called something review method, right?
Yes.
So can I use normal partial fraction, the one like the
You meant
long method?
residue method, yes?
Yeah, I don't want to use residue method. I want to use the normal one.
It's okay, use the normal one and calculate the value of variables. You are
Okay.
not forced to use the method here, but you are forced to simplify this transfer function, which is here, consists from this part, into a partial parts. Okay, so if you given such function, you need to split it into several parts and be sure that each part here can be easily found in the table, because you are going to be provided with the table of formula. Okay, so it's in order to use the table of formula, you need something which is similar to the formula that you have in the table. Okay,
Okay.
thank you. Next, this example 10 also is the same. You can just try it by yourself. The solution already there. So you have the differential equation. The first, you need to convert this differential equation by using Laplace. So you write the equation here, ys over this 2 over s plus 2, s plus 4. Then you have the poles are different. You must be sure that the poles are different and real numbers. So in this case, you are going to apply this method, which is a over b plus c. Then you find the value of a, b, c, and you find the inverse from the table for 1 over 4s is equal to 1 over 4. The inverse for this one is equal to negative half exponent negative 2t. This one is 1 over 4 exponent negative 4. So these are how to reflect each step in application to get the solution for this differential equation. The second case here, which is you have you have transfer function, or you have a function here, and this function has pools which are repeated. That means it's not just different pool. You may have s plus 2 square, for example. That means here you have two pools, but these two pools are equal to negative 2, the same value. You have s plus 5 cubic. That means you have three pools. All pools are equal to negative 5, but you have three pools, not only one pool. So in this case, you need to apply different method in order to find the partial, or to solve for partial fraction. If you have any other method to apply, you can apply. Okay, but for this method here, what we have, we need to rewrite the equation in this form, which is we write PR minus 1, BR until we reach to P1. Then you have S plus P1 to the power of R, S to P2, B1 to the power of R, because all pools are the same. You can see here B1, B2, B1, P1. In the previous one, no. In the first case, we have S plus P1, S plus P2, as you can see here. This S plus P1. This is in the first case, this was the form S plus P1, S plus P2, S plus Pn, because the pools are different in case 1. But in case 2, all pools, the pools are the same. It doesn't mean all pools. You may have two pools, same one is different. So you need to apply the both methods. But if you have only duplicated pools or repeated pools, so in this case, you need to apply this formula to simplify. BR1 over S plus P1, and here R represent here the value of, as you can see here, how to find the value of R. BR minus K, K represent like a counter here. So the general form to find B1, B2, B3, and BR is counter K. So K in the first start from is a counter, start from 0 until R minus 1. So in order to find BR here, minus k, that means if k equal to 0, it's become br. If k equal to 1, it become br minus 1. If k equal to 2, it's become br minus 2, and so on. Depends on where is the place here. This is k equal to 0, this is k equal to 1, until k equal to p1. Okay, then this value will be multiplied by the derivative of with respect to s for the function or the pool times fs. In previously, we need to multiply each pool or times the fs. S fs, s minus a fs, s minus p fs, and so on. Here, since the pools are the same, you just have s plus p1 the value of r will be changed here. First is r equal to 1, second is r equal to 2, third r equal to 3, and so on. Depends on how many parts you have. If you have 2, so you have 2 b1 and b2 here. If you have 3, you have b1, b2, b3. If you have 4, you have b1, b2, b3, b4. Okay, so we'll see through example here how to apply. This example, they ask you to find the inverse Laplace for fs equal to s squared plus 2s plus 3 over s plus 1. Don't look at the numerator. Numerator, whatever is the value, it's okay. Doesn't matter for partial fraction. Partial fraction, focus on how to divide the denominator of your function. So since here you have s plus 1 to the power of 3, that means you are in case 2. You have multiple repeated pools, which is s equal to -1, but it's repeated for 3 times. S equal to -1, s equal to -1, s equal to -1. This because this one can be right there like this way: s plus 1 times s plus 1 times s plus 1. So you have 3 repeated pools. So now what we need to do, we need to write the general formula according to this formula here. Fs equal to Ps over As equal to Pr over S plus P1, Pr minus 1, S plus P1 to the power of R minus 1, and so on. So this will be like the highest number of B, since you have 3, so you have B3 here. If it is 4, so you will be B4. So now you have B3, B2, B1. If this one is 4, so you will have B4, B3, B2, B1. It's like this one, okay? So now the form here, or the counter that we have, in the first, the counter is equal to 0. So in this case here, you have b to the power of r. This one is 3, this one is 3. This 3 minus 1. This one, the counter k is equal to 0. This r minus 1, so 3 minus 1 is become b2 over square. This become b1 over to the power of 1. So just substitute here. So now you have this one, this is the power is 1, but not return. This 2, this the power is 2. This 3, this the power is, the power is 3. Okay. Now you have this transfer function. My task now is to find what is the value of P3, what is the value of P2, what is the value of P1. From where I can get this value? From the formula that said PR minus K is equal to 1 over K factorial d to the power of K over ds to the power of K s plus P1 R Fs, when s equal to -P1. Always s equal to -P1 because we only have one pool here. So now, what is K in the first case? When I have this part, I want to calculate P3. In this case, K equal to 0. If K equal to 0, this one is B3, is like this one. 1 over, if K equal to 0, factorial 0 is equal to 1. Factorial 1 is equal to 1. Factorial 2 is equal to 2. Factorial 3 is equal to 6, and so on. So we just substitute for this value. Now here we have 1 over K factorial, which is 0, which is equal to 1. D to the, the power of the derivative here, d of k equal to 0. So that means there is no derivative. D to the power of 0 is equal to 1. Any number to the power of 0 is equal to 1 over dsk, also this equal to 1. Okay. Now s plus p1 to the power of r. What is r here? Is 3. In this case is equal to 3. So just substitute is equal to 3 times fs. So this is fs here. Substitute for s equal to -P1. S equal to -P1. So each s here will be substituted by -P1 after we multiply s plus 3. But if fs here, what is the fs? It is here. You can see this is fs. How to find this part? How to solve? How these bars become like this one? So you just multiply s squared plus 2s plus 3 over s plus 1. This is fs times, this is fs times s plus 1 cubic, s plus 1 cubic. So this part will go with that part. Now I substitute for each s by -1. So I have -1 squared, so it's -1 squared plus 2 times -1 plus 3. So it's become 1 negative 2 plus 3. 1, negative 2 plus 3. So 3 plus 1 is 4, minus 2 it is 2. So I got the value of P3 here, which is 2. I need to substitute in this here is equal to 2. 2 over S plus 1 cubic. Then I need to find the value of P2. I use the same formula. In the first case, k equal to 0 because it's a counter. So k equal to 0, then k equal to 1 here. If k equal to 1, 1 over k factorial, which is 1, same 1 factorial 1 is 1. D to the power of k is equal to 1. So it's become d to the power of 1 over d8. That means the first derivative of the function here, which is fs. I need to multiply s plus p1 to the power of r here, which is 3, correct? Times fs. So what's the function here? I have s squared 2s plus 3 because this already gone with each other. We still have only s squared plus 2s plus 3. So I need to find the derivative for s squared plus 2s plus 3. And I need to substitute later on each s equal to negative 1. So what is the derivative of s squared over ds? It is 2s. What is the derivative of 2s? It is 2. What is the derivative of 3? It is 0. Okay, so you will still have 2s plus 2, s equal to negative 1, so the value is equal to 0. Same to calculate P1, k equal to 2, because first k equal to 0, k equal to 1, now k equal to 2. I substitute for k equal to 2 here, so factorial of 2 is 2. Then I have d over ds for the previous one. That means this d over ds for the result here is represent d square over ds square for that one. Because this one I already applied one derivative, I got this one. If I do another derivative, that means it is like d square over ds square for the original one. Okay, but we already do this one. So now I add one for this result. It's like d square over ds, or the second derivative for the function. When I drive this 2s, it gave me 2. When I drive 2, it gave me 0. So I have 2 over 2, no more s to substitute here. You just put 2 over 2, so it's equal to 1. So now I have P3 equal to 2, P2 equal to 0, P1 equal to 1. So now this part will removed. I still have 2 over s plus 1 cubic plus 1 over s plus 1. So these two variable or these two parts of our function, it's easy to be found from the table and to find their inverse. So ft here is equal to t square exponent negative t. This from the table. According to the table, if you have a over s plus a square, for example, or 1 over s plus a to the power of n, then you need to apply this form. So you find it 2 square exponent negative t, and here we have 1 over s plus 1, so it's exponent negative t. Okay, so this will be the inverse Laplace transform for this one. Is it clear here? Any question about this part, about this example? This all just method to, the calculation here is just to show how we can apply the partial fraction. But our task is not the partial fraction. Our interest more on the finding the inverse Laplace transform for this function. But because it is difficult to find the inverse for this one directly from the table, we apply partial fraction. And the result of applying partial fraction gave me this function here. This fs, it is the same as that fs. But this one consists from a bar. This one is as one block. This consists from 2 blocks or 2 bars. If I ask you to find the inverse from the table for this function, you will not be able to find. If you go to find, you cannot find. If you apply the integral method and you are good in integration, okay, you can calculate this one by using integration method. But if you are not good, so better to find the partial fraction, and this is the common method that we use for inverse Laplace transform. You find the inverse method, the partial fraction, then each part from this partial fraction will be converted into the time domain from the timetable directly. Any question until here? You still there or not? I told you at least one. Partial fraction we use in applied math. Okay, good. You save the time, correct? So we can finish this chapter next week. The third method we are not going through. I mean the third case of partial fraction here. And the third case when you have root look, I mean the pools are complex numbers. The pools are complex numbers. They are not different number and real. They are not repeated real number, but they are complex number. This is the case number 3. Roots of the denominator of Fs are complex or imaginary. As I told you, our interest is not the partial fraction itself. It's just to use partial fraction in order to calculate the inverse Laplace transform for the complicated functions. If the function is already easy, no need to apply partial fraction. You just go to the table, find it. But if the function is complicated, so you need to apply partial fraction here to simplify. Okay. So the third method or the third case here, your roots are complex or imaginary number. So like in this case, for example, here you have Fs over 3 equal to 3 over s squared plus 2s plus 5. And if you try to solve this part here, which is s squared 2s 5 to find the roots, you are going to find the roots of this is imaginary number. So in that case here, you are required to solve or to find to convert this function into a part like following this formula, which is k1 over s, k2 over plus k2s plus k3 over s squared 2s and 5, because this part who generates the complex pools. Then you need to solve the value for k1, k2, k3, and you substitute here to find the imaginary one. As I told you, we are not going to have example on this part, and you are not required to do for the imaginary complex number unless if you are good in the since you already taken applied math, so you may be asked for this one. Okay. So the same, you simplify the function. It's become like consists from 3 parts. This is our main task in this course. I mean, you have the inverse. The part here is easy, so you just find from the table what will be the inverse for each part of this partial fraction function. You have here some exercise with answer. You can go and try. I mean, sometimes when I give you some exercise, either in the slides with the title in class exercise or exercise without in class. So that means and I provide the answers. So you are required to go and try to solve, because you maybe see such questions in the test or in the quiz or in the exam. So you need to try. Don't just say, oh, the answer is already here, so no need to solve. No, you have to check how this answer is come, how you can get from this function that Laplace inverse, how you can get from this one the Laplace inverse for the function. It's like all in one, okay? So no, I mean, class with tutorial are the same, because we only have 2 chapters, and we still have, we have 2 chapters, we still have only 4 weeks, okay? So I mean, we are not going to go for 1 lecture, 1 tutorial, all will be together, okay? So these are also exercises here you are required to solve. In case you try to solve this exercise, you cannot solve or you cannot get the correct answer, you can ask. But don't come to us on the night of the test or of the final exam, because maybe I already bought this one in the test or in the exam, so I am not going to answer you, okay? But during the class, after the class, between the class to the next class, you can ask. Okay, now I am going to stop here because it's already 11:45. Next week, we are going to continue with the circuit elements models, and this is one of the main application for Laplace transform. I mean, in addition to use Laplace to solve differential equation like we see before in the previous examples, we are going to use Laplace in order to analyze the electrical circuits. So please, 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 before you come to the next class, go and revise some of the theorems that you used before to analyze the circuit, electric circuit. You have already circuit analysis course, and you have fundamental course as well. So please go and revise, go through, because we are going to use like nodal analysis, mesh analysis. You may use Thevenin, you may use Norton based on, you may use superposition. Okay, so all these network theorem analysis will be used in order to analyze the circuit in the frequency domain rather than the time domain. So previously during the circuit course, you study how to analyze the circuit in the time domain. In this course, we are going to talk about how to use Laplace in order to analyze electric circuit, which include capacitor, inductor. I mean, I'm talking about the AC circuit, not the DC. Okay, I mean, you have capacitor, inductor, and you have some form of differential equations like dVc over dt, dic over dt, and so on, dBl over dt. I mean, the voltage of the inductor change with the time, the current of the capacitor change with the time. So all this will be used here, and we will see how we can use the Laplace in order to perform such analysis in a simple way, comparing with the previous one that you learned in the circuit analysis course. Okay. Any question until here? So please don't come without going through the slide. I mean, also you need to learn some techniques to use or to solve linear equations. I mean, either using the matrix, using the subtraction, using the substitution method, using the Cramer's rule. When any of these methods that can help you to do solution or to solve 2 equations or 3 equations, it will help you a lot in order to complete this chapter. Okay, so we need to have such techniques to solve 2 equations or 3 equations in electric circuits to find the variables, and also we need to have some skills in the about the theorems that used to analyze the electric circuit.